Right. Let me start. Let's review a bit from last time. So last time we talked about automata over infinite words. Right? It has the same structure exactly as finite automata, except for they're running over infinite words. Right? The input is infinite, and the acceptance is a bit different. Finite automata over finite words, you have, in order to accept, you have to reach final state or an accepting state, right? Here, an infinite word, in order to be accepted, it has to pass through an accepting state infinitely many times. Okay? So some of the states, one or more of the states will be accepting, and in order to accept the word, there should be a run over that word. Say if I take the word A, B, A, B, A, B, A, B. In order to accept it, it should pass through an accepting state infinitely many times. Okay? If there are several accepting states, at least one of them has to occur infinitely many times. So, and this is a mathematical tool, right? So one thing is that we're not going to execute these automata really. Right? We're not going to check infinite words because they're infinite. This is one thing. But the other thing is that they have finite structures, so we would use them in algorithms. We would operate on the graph structure rather than on runs of this thing. So we continued and talked about the fact that for these automata, and these are the simplest kind of automata over infinite words, they're called Cauchy automata. And I'm not going to show the other kinds. They're more complicated, but they are equivalent in what they can express. Cauchy automata, deterministic and non-deterministic automata are not the same. They show the proof, which you would see in the slides, and if you understood it from last lecture, it's good. And if you're not, don't be bothered. Okay, it's a bit of a difficult proof. My students usually, well, some of them come and ask questions, so don't feel, bad if the first time you didn't understand the proof. And it's not that important. It's just for completeness. Okay, some of the parts of this course are a bit complicated, and they're just for reference, so that we feel that we know everything. Okay. For example, if I want to say something like, always I'm not in the critical section in both processes. Okay, so I'll have a predicate B that is true when in the current state I'm not in the critical section of process 0 and process 1 at the same time. So this would be the automaton that says I'm always here. So if I'm always here, I'm always not in the critical section at the same time. I never go here because when I once go here, so as I get to the critical section, then I stay here and I'm not going to accept. Because if I'm here, there's no way back, and this is not an accepting state. Accepting states are red. So once I'm in the critical section in both processes, I'm not accepting, and that's bad. I'm not going to accept. So this is a basically non-deterministic. Well, this is a deterministic actually automaton for this property of mutual exclusion. So I can use the letters as combination of predicates, and that would be my automaton that specifies a property, similar to the specification using linear temporal logic. Instead of writing something with temporal logic, I can write it using automata. Okay? And some people like to write specification using automata, some people like to write it using temporal logic. I found, my experience is that engineers usually like to use automata, okay? And people that kind of write the design, they like the temporal logic. But we'll see that there's a point in learning these two formalisms, because the specification in temporal logic kind of more concise. It's small, it's really clear. Okay? It tells you something about what's happening when you look at it. Whereas the automata, you have to follow and to see which states they go. It's not always that clear. But the algorithms for doing model checking will use the fact that you can translate linear topologic specification into automata. So that's an advantage of this specification. I start with a temporal logic property, going to translate it, and then I'll have an algorithm. Why is it good to use the automata for algorithms? You remember that I have the state space, right? The state graph, it's a graph, okay, with edges and nodes. This is another graph. So I have two graphs. One corresponds to the system, the model, and one corresponds to the specification. And now my algorithm will consist of doing something with two graphs. It's going to be a graph algorithm, okay? Rather than something that takes a graph and compare it with some formula. So that will help me. The algorithm, you see, is based on extremely simple kind of principle. Okay, so if I want to apply model checking, what do I do? Let's recall what we did last week. So I have the system here, and I translate it into a transition system. Into a transition system, right? So I have these two concurrent processes. I have 6 transitions. And now I can construct the state graph. How I do that? I use depth first search. I have some slides. I think you get the slides, right? So you already got the slide from Professor Good. But you should get a new version with some small corrections. And also, even if you have the original version, then the relevant slides are from 1 to 171, not to 500. Okay? So not all the slides are going to cover. So I generate a state space, and how I do that, I use depth first search. Slides include explanation of depth first search. I'm sure you know depth first search, right? I'm starting with an initial state, and I just start to search forward. I take a transition and enable transition, generate the next one, the next one, etc. And at some point, I have to backtrack, right? Therefore, search, I do all the backtracking. Maybe if I completed the backtracking back to my original state, I go to the next original state, do the same, and then I'm done. I have that graph, right? It's a simple algorithm, depth first search, you get that graph. And on the other hand, you have the automata, right? So you have to compare between them. And right, I can write a specification like the one I just told you, right? That there's mutual exclusion. And I can write it as an automaton. I can translate, we'll learn all of that. You can translate that into an automaton. And then I have two automata and I have to compare between them. That's very simple. Okay? Or here's another property. I want to prove that always if turn is 0, then eventually turn is 1, right? So basically it says that each time I'm here, turn is 0, then at some point later I'm here. If I return here, again I'm here, etc. etc. We need to do that for all these expressions. So what do we want to verify? Start now to talk about model checking. We did modeling, right? First day. Then we did specification, second day. Today we do model checking. So what does it mean, model checking? What do we want to prove? What do we want to prove? So automata accept words, right? And you can talk about all the words which are accepted by an automaton as the language of the automaton. Right? Language of the automaton are all the words, all the correct sequences that the automaton recognizes. Bushy automaton recognizes all the words which have an accepting run, which have run that goes infinitely many times through an accepting state. Okay? This is the language of the automaton. So a specification written as a Bushy automaton tells you that the good sequences are those that are accepted, those which the automaton can run it and you could accept it by going infinitely many times into accept the state, right? So this is the language of the specification. In automata, we write it like that, language of the specification. And all the words which are accepted. Every word is accepted or not. So this is the word, oops, this is the language of the specification. Now, if you look at the model, right, the model you can also consider to be an automata. Let's go back to a model. Right? This is also in some sense an automata. How is it going to be a Buki automaton? Very simple. I would consider all the executions that are infinite here as the accepting execution. Okay? Another way, if you want, is I can consider this to be a Bushi automaton if I put all the states to be accepted. So every infinite execution is going to be accepted. Okay? So this is not only a graph, it's a Bushi automaton. It's a very simple Bushi automaton. It's one where all the states are accepted. Okay? So the executions of the system are those which are accepted by this Bushi automaton. Okay? Now, something very nice happened. I have two automata, one for the model, the one I just showed in the previous slide, and one for the specification. What I want to do is I want to check that the language of the model is a subset of the language of the specification. Every execution of the model is also an execution of the specification. Okay? This is my acceptance criteria. Okay? That's the criterion for acceptance. And one thing that could be a bit kind of intriguing is that I don't write equals, I write included. Why is it included? Why there's inclusion between these two? Because the specification, it just tells you what I want to satisfy. All the good executions. This is the specification. This is the implementation. This is the system. And it could be that the system is kind of made some decisions. I mean, there are several executions which are good, but it's not going to generate all of them. Okay? So it's not inclusion. I don't have to exclude. Right? I don't have to exclude some executions. I only have to exclude those executions that do not satisfy the specification, right? But there could be an execution, there can be an execution that satisfies the specification, but it's, you know, in the implementation, it's not going to be an execution of that system. That's okay. Okay? So this is an important point. This is an inclusion. Okay? That's my criteria. That's my criterion for model checking, and I have to check that. Okay? So now let's assume by a miracle someone can give me the specification. Instead of temporal logic, you would give me the specification using an automaton, a Bushi automaton. Someone else gave me the model, maybe it is compiled from the program. Okay? I have two automata, and I want to check that the language of the implementation is included by the language of the specification. This is model checking, which we're going to do. So it goes like that. If we look at the Venn diagram that corresponds to all the possible executions, okay, then there are some executions that satisfy the specification. This is the yellow executions, which are included in the red executions. Okay? And the program executions are in white, that are included, they should be included in the yellow execution. Okay? So these are the program executions, they should all be included, they should all satisfy the specification. Okay? That's the thing I want to check. If there are some program executions that are not satisfying the specification, like that, then every execution here, which is not satisfying the specification, which is outside of the language of the specification automaton, is a counterexample. In fact, model checking is more about finding counterexamples than about finding that indeed you have this inclusion. Why? Because when you do model checking, as I told you, you can have modeling errors, right? You can have that the model checker itself has some bugs. You can have that the specification is not correctly given. Okay? If someone says, he says, okay, here's my specification, here's my program, I checked it, it's correct. Are you happy? Well, you should be happier than if you didn't check, right? But there could be many problems. But if someone gives you a counter example, which is the result I want, model checking, when my model checking didn't pass, that's more information. Right? So model checking is more about showing that something is not correct. Okay? It's not that you have to find that it's not correct, it's correct. But really, it's more interesting in this. Okay, so automatic verification. As we said, the model is a graph. The specification refers to the graph representation, and we want to apply graph theory algorithm. So tomorrow we're going to learn an alternative approach to model checking that doesn't look directly at the graph. So we're going to do something which in some sense is more efficient. It's going to take care about a lot of states at the same time. We're going to use some interesting data structure and do things in a sometimes more efficient way. But today we just apply graph algorithm. Okay? So if I took my model, right, if I took the graph, say the graph for the mutual exclusion problem, I could already check things without a specification, right? If someone says an invariant, a property that should hold in every state, like mutual exclusion, I don't have really to write a temporal logic like box invariant. Invariant, you should hold in every state. Then I just can look at the graph, or I can check the graph when I do the depth first search, and I check that all the states satisfy the mutual exclusion. Okay, it's easy. I can check whether there are deadlocks, right? If I reach a state that doesn't have any successors, I don't need a specification. This is the specification. Dead. Okay? Or dead code, right? I can look at the graph, and I look at the code each time I'm in a reachable state. Remember, a reachable state is a state where I have a path to that state from an initial state, and I tick near the code, in the code near that place, in the code that I was in that place, right? So I was in non-critical zero. I tick all the places I visit in the reachable state. Those places I didn't visit, they are dead code, right? I don't need a temporal formula. But sometimes I need temporal formula, and now we want to see how we do. Okay, model checking has limitations. So initially, model checking was only about finite state systems, a system that I can describe using a finite graph. Okay? Nowadays, you can do model checking in some cases with respect to some domains which are not finite. My personal opinion that you can do it in a very limited way. Some people really believe that more and more things can be done automatically, but I still believe model checking is more about finite state spaces. Therefore, if you have an algorithm that, say, it finds the least common denominator of two numbers, okay? That's an algorithm on unconstrained integers. It's not a finite state algorithm, okay? You cannot apply model checking. Model checking is about finite states. You can apply it for numbers up to some size. You can apply it for particular numbers, but not for any integers. If you have unbounded message queues, it's a communication protocol, but it doesn't say what is the maximal size of the message queue. Probably model checking would not help you much. Other data structures, queues, trees, stacks, not model checking. If the queues are bounded, if you know that you have a finite limit, which you know the limit, you can do model checking. If it's an infinite thing, a lot of times you cannot do it. Sometimes there are particular cases, like if you have an algorithm and you know that it has only one unbounded stack, you can do model checking. There are methods that do that. Okay, it's decidable. If you have two stacks, you cannot, because two stacks can simulate a Turing machine, and Turing machine is undecidable. Okay? So there are strict limitations of what you can do there. I'm going to verify only finite state systems. Okay? It's important to not to expect whatever you cannot. Another thing, model checking has the main problem of state space explosion. Okay? You can handle many states, and we'll see tomorrow a method that can handle a lot of states. Sometimes, right? Not in all cases. It's kind of heuristics. In many cases, it's going to work better than what I will show today. In other cases, it's not. Okay? Kind of the complexity of model checking is such that it's never guaranteed that model checking would work efficiently on all examples. If you have a lot of states, then it is possible that it's not going to work very efficiently. That you're going to wait and wait and wait, and it's not going to terminate. So the main thing is the state space explosion, the number of states. And I don't want to discourage. Model checking is being used, I think, in many companies, in particular hardware companies. Intel, I don't think there's a chip for which they don't do model checking. They do it in different ways, like they take a portion of the chip, they don't take all of it. But say you have an algorithm, I said just in the previous slide, that if you have an algorithm that calculates, you want to do model checking for some kind of unbounded integers, right? You cannot do that. I said it's undecidable, right? Like the least common denominator. But even if you know that you have integers which are bounded by 32 bits, okay? And you have two such integers, right? That's the least common denominator algorithm for two integers, each one of size 2 to the power 32. If you want to really keep all the states and do this graphical thing, graph thing, then you have 2 to the power 64 states. No point in storing that, no point, right? I mean, there's no memory in the world that could store it. Time would never be sufficient, right? There is an algorithm that in many cases would work, and you'll see that tomorrow, by compacting things. It's a very sophisticated algorithm, not promising to work very well on every instance. For example, the algorithm I'm going to show tomorrow works for many cases in hardware. But if you want to verify without hardware multipliers, not going to work efficiently. That's life, okay? We need to know when it's going to help you and when it may fail. So, in many cases, if you want to do model checking, well, you may be encouraged with the fact that if you want to verify protocols, protocols are usually finite states. Another thing is that usually you don't verify the actual algorithm or program. A lot of times you verify an abstraction, a small model of it, right, that kind of represents many of the artifacts of the actual system, but it's smaller. Now again, it's a model thing. If you come and say, this is a little model, it's an abstraction, it's up to you to make a correct abstraction, you may fail. Right? Sometimes it's possible to do decomposition of program from different parts and verify each of them separately and then to compose the course. And there are other techniques to reduce the state space. So I'm going to skip this part. This is about depth search. I'm sure all of you know search. Okay. I'm going to do some skipping. Going back to my point, I have a model, right, on the one hand. And on the other hand, I have a property. Now, let me do another thing. Technically, I have a model which has possibly several initial states. Let me have a model that has only one initial state. And I can do that by, if I have several initial states, I'll just use another state, and that state I'll call init, and it will go into any of the original initial states. Now I have only one initial state. It's going to help me. Another thing I'm going to do is I'm going to now copy all the information I have in the state into the edge that goes into that state. Okay, I'm going to copy this here, and I'm going to copy that here. Why? Because a lot of time, it's not really important, but a lot of time we're used to automata that the input letter is on the edge, right? Not in the state. That's the way we use in automata, right? A, you say, I'm in a state and I do an A, the A appear in the edge and not in the state. I'm just copying such that the property would appear on the edge. It's just technical, it's not really important. Okay, so we came back to this point. I want to prove that the language of the model is included in the language of the specification. I hope I convinced you on that. And now, I don't know if you remember that from automata theory. I don't know, do you remember what happened when you want to check that the language of a model is included in the language of the specification? I mean, did you learn an algorithm to do that? A direct algorithm to do that? I'm not sure you did. Okay? In particular, if the language of the specification, if the automaton representing the specification is non-deterministic, I'm sure you didn't learn such an algorithm. Why? Because such an algorithm has a very high complexity. Okay? It's an exponential algorithm. It's exponential in the size of the automaton for the specification. And this is true for Bushy automata. But if we look at automata over finite words, then we find out that it's not so complicated, because what I can do is I can complement the automaton, right? And this is equivalent to the language of the model intersection with the complement of the language of the specification is empty. This is exactly the same, okay? So if there's a word here, which is also here, means it's a word here, which is not here, right? So it cannot be, intersection is going to end here. All the words which are here, they have to be here. If they are not, right? I mean, if they are not, if there's a word which is here and not here, then it's here, and then the intersection is not. These are equivalent in set theory. It's easy. The bar means complement. All the rest. Okay? So for finite automata, for usual finite automata, that would be kind of a very simple thing to do, right? Because how I complement deterministic finite automata, I just take the states which are accepting and I make them non-accepting, and that's it, right? Now what happens if I have a non-deterministic finite automaton, and I want to check that? Well, I cannot switch between accepting and non-accepting for non-deterministic finite automata. So first I determinize, and then I do the switching between accepting and non-accepting states, right? So for finite automata, everything is full. For Bushy automata, for automata over finite words, remember, I cannot complement, because not every automaton is represented as a deterministic finite automata. So I cannot first determinize and then switch the accepting and non-accepting. Because not always I can determinize, right? It's not going to work like that. So I have a problem here, right? Checking emptiness is easy, right? Checking emptiness of a intersection of two automata is easy. Now I'm going to repeat that. So what do we do here? So if someone gives you an automaton, a Bushy automaton, and you need to calculate that directly, it's going to be an algorithm which is not only heavy, it's going to be a very complicated algorithm, very complicated. I don't think anybody in the world has ever implemented such a check for a Bushy automaton. It's just too complicated. Doing that again, you want to do this complementation, it's too complicated, okay? Nobody in his right mind will do that. But here's what people do, it's a trick. So we assume that the specification is given as an LTL property, okay? And the LTL property is translated into such an automaton, okay? So this is my specification actually. From that I get that specification and I can translate, okay? I can translate. So what am I going to do? What am I going to do? Well, I showed you that later, but let me tell you the trick now, if you like it. What I'm going to do is, instead of taking the specification and translating and doing this very complicated algorithm for complementing, because I cannot determine it, there's no determinization. I simply would take the specification, write a not before it, that's the complementation, and then translate the negation of my property directly to that. And then that's easy. We'll go back to that. It's a trick. Okay, so what do I need now? What we're going to study today is we need to intersect two automata, right? Well, I told you that I'm not going to complement, right? I already revealed to you how to complement. Oh, this is so complicated. Actually, I don't know how to do that myself. I mean, I kind of, if you give me a pen and paper, I would sit for 2 hours. Eventually, I'll find how to do that. But it's a stupid way of doing things. You see that there's a way around it, and how to translate from LTL to a Bushido. If we know all these things, well, we need also to know how to find entries. So again, I need to translate. Well, basically I need to complement, but I will avoid that. I need to find emptiness of the intersection. Intersection and emptiness. Okay? If I know that, that's model checking. Everything. Okay. So let's start first with the intersection. That's the easiest part. Someone gave me two Bushy automata. So the Bushy automata, remember, it has states. It has alphabet. That's the input alphabet. I assume that it's the same set of letters, same alphabet. It has transition relation, okay? It has initial states, and it has accepting states, okay? Let me assume that one of these automata, all the states are accepted. There's two reasons I do that. One reason is that, remember when I presented the intersection, the problem of model checking, a model and a specification. The model was simple. The model has all its states accepting. Remember? So I can assume that this is the model automaton, and sequence is accepting if it's infinite, right? All the states are accepted. So it's an easier problem. Why not working with it? Here in the specification automaton, A1 is a subset of S1. Some of the states are going to be accepting and some not. So that would allow me a simpler case than the more general one, in which here also the set of accepting states is a subset of that set. Okay? Fine? Later, I'll make kind of the more complicated case. It's important too, but to do the simplest kind of model checking, I don't need the more complicated case. You see that for Bushy automata, there's a bit of a complication if both of them have a subset of states which are accepted. So here, all the states are accepted. So how do I do the intersection? The intersection is done exactly in the same way as finite automata. Okay? So the states, oops, it's not my regular pointers, I'm sorry. The states are just pairs of states. Right? I take the Cartesian product of the states S1 and S2. These are the states. Okay? The initial states are just a product, just pairs of initial states. Okay? So basically, what is the intersection? I'm going to run on both automata at the same time in a synchronous way, starting from initial state and using the transition relation to move pairs of states. Right? Now I make the gain of assuming that only one of them has accepting state. The other one always accepts, so the other one always agrees. It's good that when two people have to agree, one of them will always say yes, because accepting states would be determined by the guy who doesn't always agree. Right? So accepting states, would be pairs of states. The first component is an accepting state, here. The second component is any state, because this one always agrees. So you'll tell me if the pair is accepting or not, okay? This is the simplest case. And I don't need more than that to do the simplest model check. Okay? Now the transition relation would be a synchronous transition, right? Just like you do for intersection of usual automata, simple automata or finite words. I am at a pair of states, and I see A. So the first component would move according to A from x1 to x2. Second component would move according to A from y1 to y2. Okay? This is the intersection. It's completely the same as intersection of two automata over finite words, right? Nothing new here. Remember, this is intersection for a special case. And indeed, if I could, if I wanted to translate my specification to two automata and I needed to do such an intersection, because all the states in the model are accepting, that would be sufficient. Okay, good. So say I want to do the intersection here. I have two automata, and I want to do the intersection. So see, this automaton accepts in every state. So an accepting state is just an infinite. An accepting execution is just a run which is infinite, because all the states are accepted. This one has to see as zero infinity many times, right? If it gets stuck here, if it, say, does B indefinitely, it's not going to be accepted. Right? This one, I mean, all the possible states are accepted. This one is not a complete automaton, right? So you can see that it's not that it accepts everything, because kind of their assumption that I can do the move. If I'm here and I have to do an A, it kind of means that I go into a sync state and I keep doing it, right? It's not going to satisfy all the executions, but all the states are accepted. Okay, so if I want to do the intersection, here's what I get. I get states which are just the pairs of states of that automata, okay? And I got the transition that are consistent with the transition relation of that automaton and that automaton depending on the component, from S0 to S1 on a B, S0 to S1 on a B, from T0 to T1, T0 to T1 on a B, okay, from T0 to T1. Okay, maybe I have some mistake in the slides, I don't know. So far nobody found an error. So. Notice something interesting. This is a state in the product, and this is a state in the product, but they are not reachable from that state, which is a pair of initial states. So this is the initial state of this graph. So these states I could erase, right? They are not reachable. Okay? So let me erase them. And I have a simpler problem. Okay? So now we know how to do this intersection. Now let's go to the more interesting case. Suppose now that I have two automata, and it is not true that in one of them all the states are accepted. Okay? This automaton accepts on S0, and this automaton accepts on T1. Okay? So how do I calculate the intersection? Okay. Now you see that for Cauchy automata, it's not the same thing as for, I mean, we already saw that Cauchy automaton, sometimes deterministic automaton is not enough, right? There are languages of Cauchy automata which we need non-deterministic automata. And here we see the difference that intersection is not as simple as finite atomic. So what do I want to do in the intersection? So let's start with two possibilities. The first possibility is say, okay, if I have a finite automata or finite words, what would I do? It's probably, intuitively, what would I do? Well, let's try to say that a state is going to be accepting if both components are accepting. Okay? Remember, go back. Remember that before I erase these states, there will be more states, but that's not important because these states are not rich. So here's what I left with. So the accepting state would be the one which is S0 with T1, right? Both components are accepted. Okay, that would be my first intuition. Okay, S0 and T1. Now this is not a reachable state in the product. Remember, this is one of the states that we erased. Okay? So actually, I have no accepting states now. Okay? And let's see. That automaton accepts BA omega. Omega means infinitely many times. Repeated infinitely many times. Like a star, but not a finite number of times, but infinitely many times. Like BA omega. If I do a BA, it's accepted, right? Because it sees S0 infinitely many times. And if here we see BA, it's accepted because we see T1 infinitely many times. And if we do BA, it's not accepted, right? Because we never get to any state that is accepting, any state that has both components accepted, right? So the word BA omega is in the intersection of the two languages, but it's not accepted by this automaton. So my assumption that I can simply decide that the accepting states, the states which have both components accepting, is as good as an accepting state, it's a good criteria for acceptance, is not a good assumption. Okay, what went wrong? Someone can figure out what went wrong? The intuition of what happened here. Okay? So what happened here is that that automaton accepted BA omega, and that one accepted BA omega. Only that one accepted it after every even sequence. That one accepted it after every odd sequence. Okay? So both of them accepted many times, infinitely many times, but never at the same state. Okay, remember we had this, we talked about whether always eventually A and always eventually B is the same as always eventually A and B. They are not. This is exactly what we discuss in topology. Right? So, this is not a good criteria. Let's try another thing. Let's say, okay, what we missed is that this one accepted on S0, but at that time we were here. And this one accepted on T1, but that time we were here. And so let's assume that we accept that one of the components is accepted. Okay? Reasonable? Now, this one has S0, so it's accepting, and this one has T1, so it's accepting. Okay? And now what happens? Now it accepts the now it accepts the property B C omega. So this one B and C omega. Okay? Let's accept that sequence because I see that state infinitely. Often I get to that state which is accepted. Okay? But this one B C omega, it will be in that non-accepting loop. So it's not accepted by the intersection. This automaton will not accept it. Okay? This accept because one of them accepted, right? So if I did the OR instead of the AND thing, if a state would be accepted if one of the states is accepting, then what will happen is I'm going to accept the OR. Right? I'm going to accept sequences that one of the automata accepted, but maybe not the other, right? So what I want to do is I want to make sure that this one accepts infinitely many times, this one accepts infinitely many times, and possibly not at the same time. Okay? So how are we going to do that? So the idea of the general case is the following. I think it's kind of a cute idea. The idea is the following. What you do is, first of all, you construct these are two other automata. You construct the intersection, okay? And what you want to show is that in the intersection, infinitely many times you see Q0, and infinitely many times you see Q1. Okay? Possibly that would not happen at the same time. So what you're going to do is the following. You take care about seeing Q0. Once you saw Q0, you take care about seeing Q2, and then Q0, and then Q2. So you alternate. You look, you search for the next time that you see Q0, and then you search for the next time that you see Q2, and again, and again, and again, and again. It could be that you saw Q0, and then you saw 5 times Q2, and then 7 times only Q0. But if you're infinitely rich, it doesn't matter, right? So if you're infinitely rich, you could spend as much as you want. Because if I know there will be infinitely many times Q0 and infinitely many times Q2, I could give away many of them. Only I want to know that I'm checking Q0 and then Q2. And if this happened many times until this happened, I don't care, right? As long as both of them appear infinitely. So in order to do that, I have this copy. Okay? And you see in this copy, Q0 is accepting and Q2 is accepting. In order to take care that I'm going to see Q0 infinitely many times, Q2 infinitely many times, I'm going to copy. I'm going to split it into 2 copies. Okay? And in the first copy would take care that I see Q0. Okay? And the second copy will take care that I see Q2. Okay? I have 2 copies. Now what I need to do is I'm going to start with the first copy. I call it version 0. And once I see an accepting state, instead of staying in the first version, I'm going to go to the second version. And then I'm going to look for the time I'm going to see Q2. If I saw here Q2, I'm going to go back. So I'm going to take care of Q0 here and Q2, Q0 and Q2. As I said, it could be that I see Q0 and I'm here and I'm seeing again and again Q0, Q0. Now I don't care about these Q0s. When I see a Q2, then I go back here. Okay? So what I'm going to do, I have these 2 almost identical copies, except for here I care for Q0 and here I care for Q2. And what happened is that I take the transition relation and I'm going to redirect. What happens to my slides? Right. So when I catch Q0, I'm going to redirect to here. When I see a Q2, I'm going to redirect here. So instead of, if I saw a Q0, instead of going here, being in that version, I'm going to the corresponding node, but in the second version. And if I see Q2 and I have a C, instead of going here, I'm going to go to the corresponding node in that version. Okay? So I'm going to do a redirection. See that? I redirected the edges immediately after I saw an accepting state. Notice that these 2 states now became unreachable. I can erase them. But I redirect them. Okay? So I have these 2 copies. I remove all the states which are not reachable. I saw Q0, I'm here. I saw Q2, I'm here, or here, depending what I see there, right? And I go back and forth, okay? Now, which of the states are going to be accepting now? what I'll do is I'm going to keep one of the copies, say copy 0, and the state that was accepting, the state that contained an accepting component is going to be accepted. Okay? If I saw that state infinitely many times, it means that I saw all the possible components infinitely many times. Why? Because if I was here infinitely many times, I cannot move to the other copy infinitely many times, right? If I was here, I cannot stay. I have to move here. And if I'm here, then in order to get back to that copy, I have to see the accepting state. So it's sufficient to take the states which are accepting in the first copy. Actually, I could take the second copy. It doesn't matter. Okay? I think it's a cute algorithm. Again, this is the accepting state for that copy. That's the accepting state for that copy. But if I see this one, this guy, infinitely many times, it means that I was in both copies infinitely many times. Because each time I see it, I go back and forth, right? Each time I see it, it means I went to the other copy. Since I see it infinitely many times, it means I also return. It means I saw both this thing and that thing infinitely many times. All the algorithms of model checking are that simple. They are kind of based on a trick. And this is called Shweka-Plack construction. I was very surprised when I came to work in my university. There was an old British professor, and he is this Shweka who invented that. I did not realize. So this is the automata. Of course, version 0 will have the initial state. I start with version 0, and then I go back. Okay, so we know how to do the intersection. Now remember, let me go back. I wanted to do the intersection. We talked about the complementation, although I revealed to you that I don't need it really. And I need to do the emptiness, right? I want to check. Intersection will give me a graph, and I want to check that there are no words in that graph. It does not accept anything. So how do I check the intersection? How do I check that I accept? So that is the following. So I want to check that the language here is empty, or there are no accepted words. Okay? Now let's see what happens if there are accepted words. Okay? If there is an accepted word, right, it's in the intersection, it's not empty, and that would be a counterexample. That would be an execution that is in the model and satisfies the complementation of the property. So it's going to be an execution that does not satisfy the property. And as I told you before, that's the case when I'm very happy as a model checker, because that's a counterexample that I can show, hey, I found a counterexample and go and try it. Okay? And therefore, let me check whether the intersection is non-empty, give you a criteria. So what does it mean that an intersection is non-empty? The intersection is not empty, so this is a Bushy automaton, right? This is a Bushy automaton that corresponds to the intersection. And the Bushy automaton is accepting if there is an execution, an infinite execution that passes an accepting state infinitely many times. Okay? That's the definition of a Bushy automaton. Let's see. This one is accepting by, I start with that. So I go here, and I go like that. That's not an acceptable execution. If I go here, and then I go in a cycle here, that's an accepting execution because I see each one of these states infinitely many times and they're accepted. Okay? So how do I know that I have infinitely many executions? That I have accepting execution. Okay? We know that after the break. We have the 10-minute break. Great. You want me to continue with no break?
政治观。
是呢，不知道你自己带。你真的不知道，加油！他手机举得那么高，我不想给你看。还想说要不要帮你写
但是之前不是让是用那个东西发的，这个方式也不太，自己的手法就不像那个他们那种有好接。说是只能，他应该是有的，就有个叫它有 TCG 的 pass， 但是它那个只能实现可以，不像我们是那个拿一个，
要不这样。
Okay. So, what we want now to do is to check if this is an automaton and it represents the intersection of two automata, two Bush automata, whether it includes any word, whether it's empty or not. So we can check actually whether it's not empty. Okay? The same, to check for empty or non-emptiness is the same check. So it is what happens if it's non-empty? If it's non-empty, then there is a path, infinite path, that passes infinitely many times some accepting states. Okay? Infinitely many times. What does it mean? Let's look at that path. It's an infinite path, right? And some states of that path appear infinitely many times. If I look at that path, any infinite path, since the number of states, of different states of that path are finite, right? Because it's a finite automaton, right? I have finitely many automata. If I look far enough, at some point, I'm going to see only states that are going to repeat forever. If there is any state that would still appear finitely many times, let me look further. At some point, all the states would appear forever, right? Because there are finitely many states. It cannot be that infinitely many states would appear finitely many times. So every accepting state, or every run, if I look far enough, are going to be only states that appear infinitely many times. Okay? What does it mean in a graph? In a graph, it means that if I have only states that appear finitely many times, then there is a path from every state that appear infinitely many times to any other state. Okay? Since I have to have an edge between every two states that are adjacent, and these states will appear infinitely many times, there's a path from every state on that suffix of the path to any state. Now, what I can do is I can look at the graph and I can generate what's called the strongly connected components. These are the states such that there is a path from every state in the component to every state. This is a strongly connected component, and this is a strongly connected component. Okay? This is actually also a kind of a naive or a primitive strongly connected component. It's only one node. But these are the two strongly connected components. In fact, it's sufficient to look at the maximum strongly connected components. In order to work less, I don't need to look at strongly connected components, which are included in the bigger one. So these are the two strongly connected components. If there is an accepting path, then what I know is that it's going to reach a strongly connected component and stay there forever. So this case is going to, this is a strongly connected component, but it's going to exit that component, get into that component, and here it can stay forever. It's going to stay there forever, and that component would include an accepting state. Okay? So, all I need to do is I want to take that graph, after that graph was constructed as the intersection of two automata, as I showed you before, and decompose it into strongly connected components. And there are algorithms to do that. Usually depth first search algorithm actually could be augmented to do that. It's called the Taugeon depth first search algorithm. I don't know if you learned that, but it finds what's called a low point, compares, enumerates, but it doesn't matter. It's very trivial. Complexity is linear on this side of the graph. I decompose it into one trivial and two non-trivial maximum strongly connected component. Those components which are not reachable, of course, in states which are not reachable, I can throw them away. And if I have a reachable, strongly connected component that has an accepting state, then that means that there is an infinite execution that accepts. Right? So here, this component, strongly connected component, maximum one, with an accepting state, it means that if I accept, I would eventually end up in a strongly connected component, because all the states are reachable from each other from some point on, and they would have at least one accepting state. And vice versa. If I reach a strongly connected component that is reachable and it has at least one state which is accepting, I can find a path through it, and I can go through that path, right? So acceptance, non-emptiness means that there exists a reachable, strongly connected component with an accepting state. It's easy to do, okay? It's just applying this Taugeon depth first search algorithm. There's another interesting point about that. If I have a strongly connected component that has many nodes, I can have many different paths. The paths don't have to have a cycle, a simple cycle like that. Could have choices, and then I have one choice once, and then the other choice twice, and then the first choice 7 times, and the other choice 288 times, right? It doesn't have to repeat. But because it's sufficient to look at the strongly connected components that are reachable and have an accepting state, I can always find a path that enters that component, and I can draw a cycle. If it's a strongly connected component, there's a path from every state to every state. So I go from the entrance point to some accepting state, say this one, and then to the entrance point. It's always such a path, which means that I generated, or I kind of proved to you that if the language of this automaton is non-empty, there's always a path which starts with some prefix, and then it cycles. These are special paths, and they are called ultimately periodic paths. Why ultimately periodic? So they start to do some kind of different things, and then ultimately at some point they just repeat. There's a cycle. It's a stem and a cycle, stem and a cycle. What is interesting about that is that if you follow what I said closely, you see that if there is a word which is accepting by this automaton, okay? Again, this word corresponds to a counterexample, right? This is a word of the intersection of the model and the complementation of the automaton. It's a word that corresponds to an execution that is bad. It's in the complementation of the specification. But it doesn't matter. If there exists a path like that, then there exists an ultimately periodic path. This is a very beautiful property, because it means that if I have a finite state space and I do model checking, okay, there's always an ultimately periodic path, and the importance is that if I found that the intersection is non-empty, and as I said, that corresponds to having a counterexample, and I want to go back to the engineer, to the programmer, and say, look, you have a mistake, and here's an example, right? This is the useful case, where I'm not just saying, I checked it, I didn't find an error, and so I think there isn't any. This is the case where I say I found an error. Look, maybe it's wrong because I did the modeling wrong or anything. Check it. It's always that I have an ultimately periodic counterexample. It means I can present it as a finite path, a finite prefix, and a finite cycle. It's always presentable as two finite things. And that's the nice thing about model checking. I can always show the counterexample in a finitary way. I don't have to tell the engineer, look, there's a graph and it goes like this, and then it goes like that, and then it goes that. It's always that I have an ultimately periodic counterexample. Right? Okay, great. Okay, as I said, I need to find strongly connected components using Tarjan depth search algorithm. There are alternative algorithms to that. I'm not going to go into that, but if you would be interested in that area, there's an algorithm which is called a double depth first search. You start to do a depth first search, and then whenever it backtracks into an accepting state, then it does a second depth first search, trying to look for a cycle. Okay, it's an alternative, so you don't need Tarjan algorithms. So there is a kind of more simple algorithms, actually, in some case on the fly, in the sense that it doesn't have to keep all the strongly connected components, but it kind of goes along and tries to look for a cycle without keeping strongly connected components. It's nice. Okay? And already, so that I already told you. And as I said, what we need to know. We need to know how to model. We need to know how to write a specification. We would learn how to translate the specification from LTL into automaton. And I said we need to complement. And as I revealed you, we don't need to complement. Because instead of taking the property and doing the complementation, translating and doing the complementation, we can take the property, complement the property, and then do the translation. It's the same. So instead of taking the property and find an automaton that corresponds to that property, it has the same language, and then find an automaton that has the complementary language, I'll take the property and I'll find a property that is the complement. It is satisfied exactly in the cases that the property does not hold. This is very easy to do, and all I need to do is put a small negation symbol in front of the formula. Right? Another trick. And then I translate that. If I translate that into automaton, I get an automaton, a Bushy automaton, that kind of represents the complementation of the specification property. Okay, no need to complement. Complementation is very hard, and also the algorithm is extremely complicated. I don't think anybody ever in the world has implemented model checking by first translating and then complementing. Okay, this is the way it's done. So far, again, nothing complicated. I think all these things are small, nice tricks. Another thing, which we'll go through later, is that we talked about fairness. If you remember the first day, I gave you two alternative ways of modeling the system. One was with busy waiting, remember, and it added some transitions. And I said that sometimes I want also to exclude some of the executions, because some of the executions are not fair. Okay, so sometimes I would also have a fairness constraints. And in that case, I have to do the intersection of the programs, the negation of the property, the bad executions, and the fairness constraints. So fairness would say some of the execution, maybe they are bad, but they're not fair. So I don't care about these. All I care is about the executions which are bad, fair, and they are in the model. These are the counterexamples that I look at. Okay? We go back to fairness, but just to let you know that sometimes there's more component. Fairness is a difficult stuff. Instead of writing the specification for fairness, I could alter the algorithm, but it's done trigger. Okay? Let me go further. Okay, so now what we want to do is we want to translate the specification into an automaton, into a Bushy automaton. Okay? someone wants to write the specification as an LTL, and as I showed you, what I want actually is a Bushi automaton, right? Take the negation of the specification LTL. I do the translation. I have now a model. I have a Bushi automaton. The model is also a Bushi automaton where all the states are accepting. Take the intersection, and I calculate the strongly connected components and find whether the intersection is empty or not. If it's not, it's a counterexample, and it's always ultimately periodic. Okay? So far, kind of, we know, I don't know, 80–85% of model checking. Now, the only ingredient that is missing is how to do the translation. Okay? Now, the following algorithm is non-trivial. And if you don't understand it until completely, it's not a problem. Don't be worried. I mean, I think what you need to know here is the principles. Okay? Some of you would understand it completely, some would not. I mean, the guy who wrote the main model checker spin, when the algorithm was presented to him, he looked at it, he programmed it, but he didn't believe it works because it was difficult. Okay? So let's see that we understand. By teaching you this algorithm, I don't intend you later to use that algorithm, but kind of to make some kind of deeper understanding of, of linear topology and the connection with logic, with automata. Okay? So, don't be hard on yourself with that algorithm. The algorithm is doubly recursive. So, how are we going to translate? So we want to take the specification and we want to do the model checking automatically. And as I said, it's easy if the algorithm would be based on graphs. So take the LTL property, translate it into an automaton, which is graph. Two graphs, intersection. So that's the entire thing. That's the only thing we didn't learn so far. And now let's see the translation. In order to simplify the translation, I'm going to present to you a new type of automata. Instead of a Bushi automaton, I'm going to present a generalized Bushi automaton. Bushi automaton, in order to accept, you have to pass infinitely often through an accepting state. There's a set of states which is accepting, and you need to pass at least one of them infinitely many times. Okay? In generalized Bushi automaton, I told you that there are different versions of these automata written words. In generalized Bushi automaton, it has several accepting states. So you have set F1, F2, etc. N sets of accepting states, and in order to accept, it has to pass at least one state that is accepting here, at least one state which is accepting here, and here, and here, and here, and here. It has to pass through each one of these sets infinitely many times. It's a bit more complicated. Instead of passing at least one accepting state, it has to pass infinitely many times a state in each one of these sets. Okay? Why I do that? It's going to be useful in a simple way. Okay? As I told you, all these models are equivalent. Okay? There's nothing special about that. There's nothing I can do here that I couldn't do with only one state. So I'll show you that I can translate a general Bushi automaton into a Bushi automaton. Okay? But I still am going to use that, and you see by my translation that that has helped me to simplify something. Okay? So, if I have a general Bushi automaton, I can translate it to a Bushi automaton by doing exactly the same thing I did with the intersection. Okay? In order to translate okay. What I want to do is I want to take these sets and I want to eliminate them. I want to have only one set. Okay? And what can I do? I have to make sure that I see state from here and from here and from here. I do it exactly the same way as I did in my intersection algorithm. Remember the intersection case where not all the states were accepting for both automata? Then I had two versions, right? One which take care of the accepting state of the first automaton and one of the second, and I just alternate between them, okay? Here I can do exactly the same thing. I just am going to have n versions, and each time I see an accepting state here, I'm going to move to the second version, and when I see an accepting state here, I'm going to go to the third version. When I am going to see an accepting state here, I'm going to loop back to that. So if I saw overall, here's my automaton, it's exactly the same, right? This is for the case that I have two accepting states, right? But exactly the same example as before. I have two accepting states. I want to see this state, accepting state of the first version would be Q0, and here it would be Q1. So I have two singleton states, and I'm just going to do the redirection. And now I'll take as an accepting only the first set, and if I go all the way, so in this case it's just two accepting states, and I can have n of them. If I see that version infinitely many times, it means I saw each one of the accepting states infinitely many times and went back to the first one, okay? So the algorithm is simple. So just for technical purposes, to simplify the presentation, I work with generalized Bookey automaton, but at the end, I'm going to kind of get rid of the different sets, and I'm going to be left with only one according to this translation, okay? So remember that generalized Bookey, not difficult, it's not a problem, it's just to help us understand the construction. Okay, now another thing I'm going to do is I'm going to simplify the logic. If you remember my first or second lecture, I told you that I don't need all the temporal operators, right? It's sufficient to have until and next time, right? So in order to present the algorithm in a simple way, what I'm going to do is I'm going to get rid of a lot of stuff. So remember, I don't need both of these, etc. So the first thing I'm going to do is it's going to help me if negations would be only adjacent to the propositions. Okay, so if I have something like not always phi, that would be hard for me to do, because if I construct something for always phi and I have to negate it, I have to do complementation, right? So if I build the automaton for always phi and I need to do the complementation, if you remember, I told you that's very, very hard to do. So instead of that, I like to have the equivalent, which is eventually not phi, right? So what I do, I'm going to push the negation inwards. So at the end, I have negations only next to the propositions. And that would help me because I would not need to complement, right? I'll take care of the negation close to the proposition. That's not a problem. I don't need to complement, okay? So I can do that. Not always phi is the same as eventually not phi, and not eventually phi is the same as always not phi. But what about not phi until psi? Okay? How do I push negation inwards? Or it turns out that you need something like that. And these are dual. Dual in the sense that always and eventually a dual in the sense that if you have a negation in front of that formula, is the same as a negation inside of that formula. Okay? It's like and and or dual. If I want to say not A or B, then it's the same as not A and not B, right? Or vice versa. Not A and B is the same as not A or not B, right? It's a dual. In Boolean logic, it's called De Morgan laws, right? So I need a De Morgan law. I need some operator such that if I write not phi until psi, then I'm going to translate that to not phi, some operator, not psi. Okay? I need the dual of until the same way as box and diamond are duals. And I call that operator release. Okay? That's not a very useful operator usually for specification. It's not an operator that has a slick semantics like the until, but I hope there is one. So the reason I need that is because I want to push the negation inwards. To be honest, I don't need that. So I can use, instead of that, I can use an until formula that would represent that, and the negation will be pushed inwards. The only thing is that the formula would be longer. And if I push until inside until, and I do that, I keep doing that, it could be that because the formula is longer and longer, is bigger and bigger and bigger, I can get a formula which is exponentially longer than the original. Here, it's the same size, right? At most, I add a negation. Okay, so at most the formula could be like less than twice as big as the original. So I need that release. I call it release, or R. And it has the following not very nice semantics. It has two possibilities. There's two possibilities. It says P release Q, which means either Q is never true, either either P is never true, right? And then Q has to be true forever, or it could be that at some point P is true, and that is the last state where Q really needs to hold. So if P doesn't hold, if P never holds, then it does not release Q. Just Q must continue holding. But if it sometimes holds, then that's the last state where Q has to hold. In the next state, I don't care if Q holds or not. I don't know if you think this is, you know, if you got the semantic like intuitively. I find it non-intuitive. The point is that this definition corresponds to the dual of until. And it's just a technical thing, because if I use a release, then it's good. I think also, I hope I'm not saying rubbish, if I remember, someone asked me, says, with until, if I say true until Q is the same as eventually, true until Q is the same as eventually Q, and someone says, what about always? So I think it's P release false is like always P, because it's dual. Okay? I'm not sure. I mean, you should check it if you care. Has a non-intuitive semantics, right? It has some, I mean, it's called release because kind of here, P did not release Q. And it didn't hold anywhere, so Q has to hold forever. Here it did release it. It's not like until, because first of all, until P until Q has to happen. Here it does not have to release it. If it did not release it, the other one holds forever. If it did release it, unlike until, on that state, it still has to hold, and only in the next state it doesn't have to hold anymore. This is what it is, okay? Except that just mathematically, this corresponds to the semantics of the dual element. And, you know, here's the use of De Morgan law, right? So now, I do that, I push negation inwards, 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 and now I have only negations next to propositions. Okay, now I get rid of all kinds of stuff, like implication, I don't need to write implication, right? I get rid of eventuallys and always using the theory. Oh, here's the correct thing. Sorry. Always phi is the same as false release phi. Okay? I said it wrong before. I said phi release false. It's false release phi. Okay? Why? Because false never does the releasing, right? So as long as it doesn't happen, the second one really has to still keep happening, right? So that's the first. So now all I have is I have next time, I have until, and I have release. Negation only appears in front of propositions. Okay? That's all I have. So if I have something like always eventually P implies always eventually Q, First of all, I eliminate the implication. I just want and or and not. I eliminate the box and the diamond by replacing the box with the release and the diamond with until. And I push negation inwards, right, repeatedly. And I got this formula. It has until, it got Boolean operators, and negation only appears in front of a proposition. Okay? So these are simpler formulas. And now I want to do the translation. And first of all, let me show you the data structure of translation. So when I do the translation, it will help me to have the following data structure. It's going to be a recursive translation. So at each point of the translation, I have this data structure where this is something that is going to be eventually a node in the automaton graph, but it's not necessarily a kind of a node. I mean, it's somewhere in the middle of becoming a node. Okay, it's not a butterfly. It's called the thing that becomes a butterfly. So okay, it's something that is something temporary, and it will become a node. And so it has these fields. First of all, it has edges that go into it. So instead of looking, usually when you take a node, you look at which edges go outside. Here I look at the incoming edges. It's going to happen. And then it has 3 fields corresponding to subformulas. And the idea of these fields is the following. I start with some subformula here, in new. I'm going to process it. After I process it, I may get some new subformulas here, but after I process a subformula, I move it to old. Old means that subformula, I don't have to take care of it anymore in that node. Okay? These are going to be the subformulas here that I processed. These are going to be those that I already took care of. And these are going to be subformulas that the successor node has to take care of. Right? If I have, say, next time P, but what would happen is that if I have here next time P, that would mean that I took care of it, so I'll move next time P from here to here. But because of next time, I'll put P here, because now next time P means that the next node has to take care of P. Okay? So intuitively, these are the things I have to take care of. These are the things I have to take care of. I already took care of. And these are the things that in the next state I still have to worry about, and I have to do something with it. Okay? The successor state would kind of be born from the subformulas that are right here. Okay? These are the elements, and of course every node will have a name. Okay, G13. And here's the main idea of the transformation. All the transformation, there are different kinds of transformations of linear temporal logic. The classical transformation, which is different from this one, is always exponential. So that it always would generate a graph which is exponential in the size of the formula. This one is not necessarily exponential, so it's better. But the idea is always the following. It says, if I want to write phi until psi, this is equivalent to the following. It means either psi is true now, okay, or phi is true now, and phi until psi is true in the next state. Okay? Either already I satisfy psi, and then I don't have to take care of anything, or if I didn't satisfy it, then I still have to satisfy phi until psi from the next state, but at least I have to have phi augment. Okay? So it's kind of unwinding. Phi until psi is either psi, or phi until psi, or phi and phi until psi in the next state. And I could replace that with the same formula and replace it many, many times. Okay? So that's called it's a recursive formula. Okay? By the way, it's not, phi until psi is not the only formula that has this that has this equivalence. This is what it's called a strong until, in the sense that psi has to hold at some point, but leak until, if psi, it does not guarantee that psi has to hold. I mean, a formula that does not satisfy psi ever also satisfies that. So I would also need to take care that psi actually holds. Okay? So this is one formula, and release is the dual, so it's not surprising that it satisfies that. It means that psi holds now, and either phi holds already now, okay? So phi released psi, but if it did not release psi, then in the next state the same thing has to happen. This is what's called a fixed point formula. It's kind of a formula which is recursive and will have a finite solution. Okay? And what it tells you, this formula, what is nice about this formula, is that it tells you how the automaton would work. What the automaton would do is it would try to satisfy psi now. Or, if it didn't, then it would try to satisfy phi now, and it would defer phi until psi to the next state. Okay? Intuitively. And I'm not going to go over that, it has the same intuition. Which means that if I have to take care that phi until psi holds now, what I'll have to do is I'm going to split this into two cases. In one of the cases, I have to take care of psi, and the other, I have to take care of these two. And in that case, there's something I have to take care of now, and something I have to take care of next time. If you remember my data structure, okay, that's exactly where I put something in next. I take care of something now, and I take care of something in the next state. Okay, that's why I need that. And when you have an OR, then that splits the considerations into two nodes. So what would happen is that I have that node, and that would be split into two nodes. Okay, when I split a node into two, what I'll do is simply, it's like a non-deterministic choice in an automaton. I'm going to copy that into two nodes. Okay, one will take care of the left part, one of the right part, and I'm going to copy the next part and all the incoming. So the previous nodes would have edges to two successors instead of one. Okay? Then let's see how it works. So I take one formula from nu, from the field nu, and I add it to all because I take care of it. And according to that formula that I took care of, I either would split that into two nodes, two brothers, they would have the same predecessor, or I just, if it's an OR. And if it's an AND, I'll just have two new subformulas. Let's see how it works. Right, so if I split, I copy all the fields, right? And then I take care of both of them. Or, sometimes I don't split. If I have, say, A and B, then A and B would go from new to old, right? And new would have A and it would have B. So it kind of has to have two goals. It has to satisfy both A and B. Here are the cases, okay? So if I have phi until psi, remember that subformula? Phi until psi is the same as taking care of psi. That's an OR formula because the operator here is OR. One copy will take care of psi, and the other copy will take care of that part. Okay, so I'll split it into two copies. I took care of phi until psi. I took phi until psi from nu. I put it in O because I took care of it. But instead of that, I put in nu. I have two versions of that node. In one of them, I'll put psi. And in the other one, I have to take care of that. So I put phi in nu and phi until psi in the field next. That means this thing I have to take care of now, and that thing is in the field next. The field next, the successor node would have to take care of. You'll see in a moment how I take care of the successor node. And the same goes for the release. So the release looks like that. So release, I have to take care that the current node would satisfy phi, psi, and either would satisfy phi or it would satisfy this thing. So actually I could write it as psi and phi, or psi and next time phi until release psi. So one node, I split the node to phi until phi release psi. One copy would take care of psi and phi. The other copy would take care of psi and next time phi release psi, which means that phi release psi I'll put in next because it has this, when it has a next time, I put it in the next field because the successor will take care of it. How does it look? See in a minute. If I have phi or psi, then I do the splitting. Again, each time I'll take that subformula from new, I put it in old, and now I do splitting. One copy will take care of phi, the other copy will take care of psi. If I have phi and psi, then I don't split. I just put phi and psi in old because I took care of it. But instead of that, I put in new phi and I put psi. If it's just a proposition or a negated proposition, I just move it from new to old because there's nothing I have to do. I just put it to old. And if I have next time phi, it means that I have to take care of phi from the next state, so I put it in the field next. Okay, that would be the basis of a successor node. So here's my property. A until B until C. Okay? So if I look at the table before, it says I have to take care of two cases. One in which B until C holds now, right? And one in which A holds now and B until C holds in the next state. So I split it into two copies. One, first of all, I take that and move it to old because it's old now. I took care of it. And then in one copy, I take care of B until C. Okay, it's sufficient that I satisfy B until C now. And in the other copy, I take care of A now. And the entire thing goes to the next state because if A holds now, but not that part, then in the next state, A until B until C. That goes to next. I still did not generate the successors, right? I still have these. And now, if I have a proposition, I just push it from new to old, and that's it. I don't have to take care. But here, I have a temporal formula, a subformula of the form B until C. So what do I do now? What do I need to do now with this node? What do I need to do with this node? Because I have B until C. Split. I need to split this as well, right? Now I split this guy. You see? So in one copy, I take care of C immediately. In the other copy, it's B now, and B until C goes to next time. Now, the B, I just move from here to here because it's a proposition. If it's a proposition or negated proposition, just move it. That's it. And here, I move the C from here to here, and that's it. So I have different nodes. These are nodes, okay? So, when do we stop splitting? So we stop splitting when the field new is empty. So if I push B from here to here or C from here to here, then new is empty. It means there's nothing to do with that node anymore. Okay? It's a node in the. It's going to be a node in the automaton graph. Okay? So when I stop splitting, I need to do the following thing. I have a list of existing nodes. These are the nodes I created during the algorithm. I have a list of them, okay? And it could be that already I have a node which has exactly the same elements in the fields all the next. It could be that I already generated such a node. Why can this happen? This can happen when there's a loop in the graph, okay? It could be that that node is kind of, I generated successors and it was generated from a father which looks the same. It means there's a cycle, okay? So if there is such a node, all I need to do is to take the two nodes, both of them have incoming edges, and I'm going to unify the incoming edges. So I'm going to update the incoming edges of one of them, including the incoming edges of the other. I'm going to just unify the incoming edges and put one version. I don't need both of them. Okay? It means I could get to that node from different directions, and I'm going to now direct all the possible directions that they can get to that node. And if not, I'm just going to add that node. Okay? It's just, so I have a list of such nodes and updated incoming edges. Okay? Now, if it's not a node with incoming edges that I updated, it's a new node that looks like that. It's not one which existed, I just updated the incoming edges. If it's a new node, then now I have to take care of the next field. And what I do is, if it's just put in the list of nodes that are finished, okay? Again, if it's not one of those that it already existed, it's just, I could get there again from different directions and I added them to the incoming edges. If it's a new one, the first time I see this kind of node, then I generated a successor and I copy the subformula here to the new here. Okay? Because now I take care of the next subformula. This corresponds to, if I'm here, I have to satisfy next time this thing. Next time means that I have a node that satisfies A until B until C, a successor node, right? But this generates a successor, and I start recursively doing the things with the successor. Okay? Notice what happened here. I have a node, I have a list of existing nodes. Okay? They are existing nodes because the field new is empty. I already processed it completely. I don't need the new anymore. If it existed, it means I reached it again maybe from different directions and I add the new directions and I leave it because I processed its successor. If it's the first time that I see a node with these two fields, then I need to generate its successor. So I generate a new node, a path, a new edge from the old version to its successor. That's why I have incoming, right? Because I connect it through an incoming edge and I copy that value from here to here. Okay? So that's what I do. As long as I can do something, either I could process subformulas in new, or I have to generate new successors. As long as this happens, I keep doing that. Eventually, that would end. And what I'll get now is I get a bunch of nodes. I have incoming edges, okay? And the only thing I need to take care of at this point is that in the field old, I look just at the propositions and negated propositions. These are the things that have to be satisfied by a node in this automaton. I mean, this is going to be the Bushi automaton. And if I'm in this node, I have to satisfy the propositions and negated propositions. I can forget at this point all the until and release subformulas. Okay? So now I have a graph. Now I have a graph. Here's the graph that I get for the formula A until B until C. This is now one thing is that how do I start this process? Okay, so I start this process by having a node which has my entire formula in new and it has an edge from nowhere in incoming. An edge from nowhere would mean an initial node. Okay, like in my other figures, an edge from nowhere is initial, okay? So I keep these edges from nowhere and they are the input, the initial states. So these three are going to be initial. Remember, I split it twice, right? So I have three, and I have here the successor. This is empty because it doesn't have to satisfy anything, okay? And I have now the structure of the automaton. So actually I have now this automaton, and this is going to be at least part of my translation. So now I have a problem. This almost satisfies the property. It takes care that if I want A until B, then either B happens, and if not, it defers A until B to the next state, and the next state, and the next state. Unfortunately, if I have something like A until B, it doesn't mean that B has to happen eventually. It could be that I'm on a cycle where I defer it and defer it and defer it, and B does not happen. Okay? So the problem is that it takes care of successive states, but it doesn't take care of untils. Until, if I say A until B, let's see, if I say A until B until C, then at some point B until C has to happen, right? Like here, B until C happens. And if I say B until C, at some point C has to happen. Okay? So this is not a complete story. What I need more is to make sure that each subformula of type until, and I have two subformulas like here. This is an until subformula, A until B until C, and this is an until formula, B until C. They are inside each other, but there's two. Okay? So I have to take care that the untils are going to be satisfied. Okay? How am I going to do that? What am I missing? This is an automaton, but why is it not a Bushi automaton? It doesn't have accepting conditions. Right? It doesn't have an accepting condition. So what I'm going to do is, for each one of the until subformulas, I'm going to generate an accepting set. That's why I have the generalized Bushi. It's easier for me to tell you how I'm going to do an accepting condition per each until subformula. Okay? In this case, this is a subformula of type until and this one. So I have two sets which are accepted. And then I'm going to, from that I'm going to convert it into one. Okay? So that part I'll do after the break. Great. I was told it's 3 hours today. This one? Exactly. This is the This is really has a different logic, different branching of CTO. There are properties you can say CTO and CTO and vice versa. What happens is that the algorithm CTO is easier. You don't need to translate. Okay, look at yeah, I mean, the algorithm for CTL is easier, but a lot of properties cannot say always eventually. At the end. everything the algorithm is exponential in the size of the property, CTN is linear. Some comparable. People have been debating that for 20 years. There's so many papers. Papers like CPS strikes back, it's like the war. It's gone.
这样那个
要不直接去三楼更好。
现在我们换3块钱。
好像那些人去安徽了。是的。那个老师是我那个带头的老师。
好像很多地方的人过来。
你去那个。
Wow. So again, I wanted to remind you, this is a difficult algorithm. If you do not understand it, all the way. It's not a problem. Okay? But it is in the slides, it is in the book, and even if you don't understand it completely, it's not that important. Right? My wish is that you get some intuition about how this works, and that it is possible to mechanically take a property and to translate it into a code. Okay, that's the main thing. And kind of the principle. The way the algorithm works, as I said, people have problems with this algorithm. I remember even Ed Clark, who's the guy who invented model checking, he had problems with this algorithm. And there's other algorithms that are not much more simple, but less efficient. This one is kind of, in some sense, it's doubly recursive because it's recursive on the size of the formula, and also it's recursive in handling loops. So it's not an easy algorithm. And another thing is that even if you don't understand fully that, it doesn't mean anything about the rest of the course. You would understand. I mean, the things that follow are easy. Okay? Don't worry about them. But let me complete that so that at least we feel that we have some kind of good feeling that we saw everything about logic. Because if you know that and the rest of the things I talked today, you can even implement your own model checker, right? You know everything about what is called state-based model checking. Model checking that goes state by state, that uses graph algorithms. And tomorrow we're going to do something else. We're going to see another logic which doesn't take state by state, but sets of states. It uses a data structure which is called a BDD, which is kind of a binary diagram for representing states or representing Boolean formulas, and it will have different principles. Okay, let's complete that first. So I have these states, and what I have to guarantee is that if I have this subformula here, I have to eventually satisfy B until C. Let's see what happens. If it's A until B until C, right? If it goes on and on and on, it would not disappear. The right-hand side, the B until C, is not going to disappear until I see a B until C. Okay? So if I go here, I see a B until C. So now it's okay. I satisfy the A until B until C because A was holding, according to my construction, A and A and A and A and A, and eventually I have B until C. The right-hand side is good. I satisfy A until B until C, right? A, B until C. And the same here. I have B until C, okay? I have B until C. If I go here, it still satisfies B until C and B, but I have to satisfy C. I have to satisfy the right hand. If I don't satisfy the right-hand side of the until, the construction would, what it would do is that the next state would also require B until C to hold. Okay? So from here, what happened is that now it's okay because I satisfy the right-hand side, C. Okay? Now I satisfy B until C. Now what about this guy? This guy, now once again B until C, but already it satisfies C. So the next state doesn't have to satisfy anything. So how do I write the acceptance conditions? The acceptance conditions are a set of acceptance of state, set of sets of states, such that for each until subformula, okay, I have two subformulas of type until. A until B until C and B until C. For each one of them, two things are good. Either I don't require that entirely. I don't care. But here I want A until B until C. But here I don't need A until B until C. It's okay. Here I want A until B until C. And here I don't. Here I want and here I don't. Okay? The first line, there's a request that A until B until C would hold. The second one, no request. So if there's no request, it's going to be accepted for that subformula, because I don't care. But if I'm going to see an A until B until C here, there is a request, then at some point I want to see the right hand. If I see it immediately, like here, A until B until C, and I have the right-hand side, then okay, it's immediately accepting. But if I don't, then I need to accept in the next state or later. So let's look at the two subformulas that I have. Okay, and this one. And this one, what happened here? Okay, this one, let's see what is accepting. So, A until B until C, is that accepting? So it depends on which, it depends on what I want to accept. Let's do it for B until C first. This is for B until C, this is accepting. Why? Because I don't require B until C. This one I require B until C, and I don't satisfy C, so it's not accepting for B until C. This one, I require B until C, but I already see C, so it's accepting for B until C. This, I want B until C, I don't see C, so it's not accepting. This one, B until C, I see C, it's accepting. This one I don't require, so I'm accepting. Okay, so for B until C, the states that are going to be accepting are this one, and this one, and this one, and this one. Now for A until B until C, okay, for A until B until C, let's see. Here I require that formula A until B until C, but I don't see B until C, I'm not accepting. This one I see B until C, so I'm accepting. This one I see B until C, so I'm accepting. This one I see B until C, I'm accepting. And this one I see B until C, and I'm accepting. And this one I'm accepting because I don't see the requirement A until B until C. So I have two sets of accepting states. One would take care that the B until C would be satisfied either because there's no requirement or C holds. So for the B until C, the accepting states would be this one, and this one, and this one, and this one, and this one. And for A until B until C, the accepting are going to be this one because of that, and this one because of that, and this one because there's no requirement for A until B until C, and that one and that. Two sets of accepting states. And now, remember, I generate the Bushy automaton with only simple Bushy condition by doing this transformation, right, with the many copies. And now I get let's see. So here's the acceptance for B until C. Okay, this is accepting for B until C. Either it has C, or it doesn't have B until C. Right? This is one set. This is acceptance for A until B until C. Either it has B until C, or it doesn't have the entire thing A until B until C. Two sets, right? Now I want to combine them into one set. How do I do that? Remember, that was the construction that has different copies. Has two copies. One copy will take care of these accepting states, and once it sees an accepting state from here, it would redirect the graph into that copy. And once you are in any accepting state here, instead of remaining in that copy, it would redirect it to this copy. So it goes back and forth, remember? And the accepting states are going to be the states of one of them. I need just one of them to have accepting state. It means that I pass infinitely often between the two copies. It's not that complicated, but I'm not sure how to do it. So this is the entire state graph, right? Without the acceptance, and then I add acceptance according to Okay? And then I do the transformation. I did not write how it looks like. I do first, whoops, this is the graph without the acceptance, right? And there are two acceptance conditions. So I need two copies. So in general, if here I have this many states, then I have a graph which is double that size and very complicated to demonstrate. But you get it automatically. Okay? Now, the spin system. So usually when I teach, I give examples and I teach the spin language, but I don't have time in that short course. Plus there's not enough time for you to look at it and to study it. But if you're interested in this area, then there's the spin tool, and you can copy it from www.spinworld.com. It's a slide in your set of slides. And there's a graphical interface. I'm sorry, it's now called iSpin. It used to be XSpin, but now everything is called I, so it's iSpin. And you can run it. The language is very simple. It's a very general language. It's model checking exactly according to the principles I showed. In fact, the algorithms there are the algorithms that I showed. Okay? It does exactly these things. The translation, the intersection, finding, the counter examples, etc. These principles. Okay? And if you like to play with that, straight, you can copy it, you can play with that, you can see how it works, right? So I recommend it. Let me go into some other issues. Okay, so let's forget for the moment, or let's forget now this very complicated translation. Again, I was interested to show you that there exists a translation, and it's pretty complicated. And go into other side issues about model checking. Remember this issue about fairness. Now we talked about the fact that sometimes there are executions which are unfair, and what we want to do is we want to check only the fair executions. So let's see a concrete example. My first model was a model of a very simplistic algorithm for mutual exclusion. And here's a good example. This is called Decker's algorithm. I don't know how many have heard about Decker's algorithm or Dijkstra's solution for mutual exclusion. Nobody? Okay. One? Only one? Two? Three? Okay. So Dijkstra was the guy who kind of, I would say, took care of mutual exclusion. He defined the problem, although he did not invent it, right? He worked in a Dutch company called Burroughs, and he kind of saw that people in distributed computing needed that. Okay, so we identified it, and this is what a lot of times referred to as Dijkstra's solution. Only it's not a solution by Dijkstra, it's a solution by a guy called Decker. And the idea is that we have two processes, P1 and P2, and both of them want to get to the critical section, but not at the same time, right? The same property as before. But what was wrong about the previous solution was that if one of the processes didn't want to get any more to the critical section, the other one could get once more to the critical section, but then it couldn't anymore, because they had to change the value of the variable term from one to the other, right? Like ping pong. Right? They have to alternate. And this is a solution that does not require alternating. And the idea is the following. So you have the loop. See, the algorithm is much more complicated. It has this loop. And what happened is that now instead of just the variable term, there are three variables. One of the variables is term. Term, again, tells you who has priority into getting the critical section. Okay? But now it has also two variables. Each process has its own variable C. C1 for process 1 and C2 for process 2. Okay? Two variables. And what happened is that initially these variables are 1, And when a process wants to get to the critical section, it's going to lower its own variable. Say P1 wants to get the critical section, it's going to lower it from 1 to 0. Nowadays, we would have actually reverse it. I mean, say I want to get the critical section, it was 0 and now it's 1. I guess Dijkstra or Dekker had the idea of being in a race and someone is taking the flag and doing something like that. So lowering it from 1 to 0. 0 means I really want to get to the critical section. Okay, it's a bit unintuitive, but this is how it is. So each process does something non-critical, and then it says, I want to get to the critical section. They are completely symmetric. I'm going to go over one process. I want to get to critical section, and so I'm lowering C1 to 0. Now what happened there, they have similar structure with the term. But what happened now that they're not stupid. What they do is the following. If one of them wants to get to the critical section, so he lowers its variable to 0, he then checks what happened with the other guy. If the other guy also wants to get to the critical section, because he also has the value C2 0, because it went from here to here, right? So what happened? Both of them wants to get to the critical section. Only if they know that both of them want to get to the critical section, then who would get there? The one which has priority, the one the turn points to it, right? So if turn is 1, and both of them want to get to the critical section, this one is going to enter, and if it's 2, then this guy would wait. Okay? Now, if this guy wanted to go to the critical section, and the other one he checked and the other one didn't want to, then it means that he tried to get to the critical section earlier, right? The other one is not, or it gave up, or it gave it its turn. Then it just proceeds into the critical section. So skip that loop, and it proceeds here. But if this guy says, I want to get the critical section, and the other one also needs to do that, then he does this while loop. And that while loop says, while the other one also wants to get to the critical section, check the variable term. And if it's the other's turn, then what you do is you took the flag that says, I want to get to the critical section, and raise it. So I'm giving up now. Instead of 0, I set turn to 1, which means I'm not interested to get to the critical section. And I'm waiting until turn equals 1. Okay? So I'm waiting until turn equals 1. So now what would happen is, like in the previous algorithm, I gave up, right? I'm a gentleman, I gave up because it's the other one's turn. I'm not going to insist. But once turns becomes 1, then I'll be in this loop again, okay? I'm going to check. But what will happen is that the other guy now, if he also wants to get the critical section, symmetrically it will give up. And because of that, eventually I'll be getting to my critical section. So that's the algorithm. It's not the most trivial in the world. And exactly for that, they invented model checking, because you can do model checking with this on this algorithm. And indeed, I give that algorithm, I used to give that algorithm for my students to check using model checking. So that would be a really nice project in Spring. So once they learn the Spring language, it's really easy to translate that into the language of Spring, which is a strange language called Promula, process modeling language or something like that. And once my students try that, they figure out that the property that says that if I want to get to my critical section, then eventually I am in the critical section, does not hold. And they are very surprised. And the reason is that there's no fairness. So there are some executions which kind of are strange. Now what can happen here? In principle, this looked like a very gentlemanly thing, right? I want to get a critical section, I check about the other guy, and I'm going to insist if it's my turn, and if it's not, I'm going to wait, right? I'm going to give up at this point and just wait until it is my turn, and then I know I can continue. Okay? But what can happen is the following. Let's see. Oops. What happens is the following, right? So I start my loop. This guy wants to get a critical section. That one wants to get a critical section. Now this guy, what he does, he checks and sees that the other one also wants to get a critical section. Okay, at this point, turn is 1. So it says if turn is equal to, okay, but no, turn is 1. Okay, if turn equal to. So in principle, you would imagine that since turn equal to, so turn is not choose, turn is 1, what would happen is that this guy would set turn, this guy, it knows that turn is 1, it's not its turn, so all he needs to do, basically, is he needs to set, this guy would, turn is 1, so this guy would give up entering the critical section. He's going to check it, right, and it's going to be here, and then it's going to say, I'm giving up C2, right? C2 equals 1, it means I, process 2, don't want to go to the critical section, okay? So you would imagine now, this one says, okay, I want to get the critical section. Does the other one want to? Yeah, okay, let's see what happened. Turn equals 2. Now, this guy is in the loop, waiting that the other one would put the flag C2 up, right? Let's go again. This guy, turn equals 1. So this guy, it waits, right? If turn equal to no, it's not. So it is in that loop, waiting that the other guy, what the other guy does, want to get the critical section. The other one wants to, yes. Turn is equal 1. It's not my turn. Okay, I give up, and then I wait that it's my turn. Now, once this one gives up, this one will get out of its loop, right? And it will go here. Because this one, if turn equal 1, it is insisting, and it's going to execute that loop until the other one gives up. And this one, very nice. This guy only, checks. I want to, the other one wants to, it's not my turn, I give up. Okay? But if you do model checking for that, you find out that you will not get to the critical section. And the reason is that it is a very strange reason. It's a bit funny, but this is what happened. The reason is that according to the interleaving model, what can happen is the following. This guy, what he does is, he's in this loop, and he knows it's his turn, so he's waiting on that loop. So he's here. He's waiting on that loop, okay? Now let's suppose the other one is here. All it needs to do is it needs to go here, check that both of them want to, check the flag, and give up his flag. Sorry, check turn and give up his flag, right? And once he does that, this one would continue because C2 would become 1 and this one would go to the critical section. But because this one really takes all the cycles, it's nagging, is it my turn, is it my turn, is it my turn? But it doesn't allow this guy, which has nothing to do but to give up and to decide not to get to the critical section at this point. But this one takes all the cycles, right? So they are kind of concurrent, but the simple move of that algorithm, just going from here, tuck, 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 it is eliminated because our model of interleaving says at any point choose an action. It doesn't say which process chooses an action, and it doesn't limit the same process to get all the actions if it can work forever, even though it doesn't do anything useful here. It just needs to be, it says, give me 3 cycles and I'll just allow you to get to the critical section, but it doesn't give him a single cycle. So it's not fair. This is what is called unfair. And this causes problems in model checking. This is very unfortunate. And the reason is that if you don't assume fairness, this classical algorithm does not work. right? If you do model checking without fairness, this algorithm is incorrect. This is a bit funny. I'm not sure. I mean, I never met Dijkstra, although we kind of lived in the same city in Austin. It was in his last year, but at least the guy who programmed Spin, John Holtzman, Dijkstra was his examiner for his PhD, and he said Dijkstra did not believe in fairness. I don't know. I mean, if he did not believe in fairness, he could not have presented this algorithm. Without fairness, this thing would not work. Okay? So, what you need to do, you need to do model checking, but to eliminate the non-fair algorithm. Right? It means you need to do something a bit more complicated. This can be done in different ways. One of the ways could be that you can specify the unfair executions. And that's going to be really, really difficult because the formula is going to be huge. And the other one is you can alter the algorithm so that the algorithm itself will only give you counterexamples when they are fair. Okay? And this also depends on the kind of fairness. There are all kinds of fairness conditions, and some of them, the algorithm would be really difficult. Okay? Difficult, complicated, complex, whatever. But let's look a bit into it, just to understand that. Right? So, if I have my executions, only some of the executions are fair. So there are different definitions of fairness, and unfortunately, again, as I told you, what is an atomic transition? An atomic transition, I mean, it's you who's doing the modeling decides what is an atomic transition, right? So what is a fair execution? You don't really know physically what the system will do, right? But you have all kinds of conditions and you say, oh, I think it's that kind of fairness or that kind of fairness or that. There are many, many conditions. And if you do the wrong modeling, then it could be that you didn't exclude enough executions, okay? So you'll find kind of counterexamples, but they are not fair. They're never going to happen in real life. Or that you excluded too many executions. So you said, there are no errors, but there are executions that are unfair. But let's look a bit on some possibilities of fairness. So I have 4 definitions of fairness. There will be weak fairness and strong fairness. Weak fairness means that something can be done from some point on, but is never taken. So it's not fair that you can do something in every state from some point, but you never take it. This is weak fairness, okay? And strong fairness means that something can be done infinitely many times from some state, maybe not in every state, but infinitely many times, and never take it, okay? So there's weak and strong fairness. And also you can say, what is this thing that can be taken? So either you look at the transition, from some point on, a transition is enabled but never taken. Or you can look at the process. For some point on, some transition of a process is enabled but never taken. Or you can say transition fairness or process fairness, and you can say weak fairness, which means continuously from some point, or indefinite, meaning that infinitely many times. Okay? So, how to use fairness? One way to use fairness is to assume that some property, some fairness doesn't hold. Okay, let's do this. Let's see an example. So I have here a program. Actually, it's written in Spin. So it has 2 processes, P1 and P2. These are the transitions. So let's see what happens, just to demonstrate the fairness conditions. This process, what it does is it sets x to 1. That's it. Let's assume that initially x and y are 0. The only thing it does is it sets x to 1. This process is a bit more complicated. It has a loop, okay? And then it checks, this is spin, it checks if y is 0, then it enters that loop. It has two choices, non-deterministic choices. Either it does nothing, or it checks if x is 1, then it sets it sets y to 1. Okay? What happens is that you see if it's here, sets y to 1, then it wouldn't be able to do that again, right? Because this is a loop. If y becomes 1, then this is not possible, right? So in fact, the loop would deadlock. I mean, you wouldn't be able to do that. Or you could say terminate it, okay? Deadlock or terminate, depending if you like it or not. But in order to terminate that loop, what it does have to do is to set y to 1. In order to set y to 1, x has to be 1. In order for x to be 1, it needs to do p1. Okay? Now let's see if this happens. Okay? And through that, see these definitions of fairness. This is just a transition to these are the transitions that correspond to this program. So let's see. So what can happen? Does the loop terminate? As I said, terminate to deadlock is the same thing. In order to terminate, y has to be set to 1, which means that x has to be set to 1. Okay? And suppose that this process starts and forever it steals all the cycles. So there's a loop here and it checks y equals 0. Yes, it is initially. And then it takes all the cycles. So it has this is a non-deterministic choice, okay? And say selects the true, so it does nothing. It's just loops here. This one, it's not fair, so it doesn't get to proceed at all, right? So in that case, the loop can be infinite, right? So this is a possibility that the loop is infinite. Let's assume some fairness conditions. Under weak transition fairness means that if a transition could be executed from some point on continuously, then it's going to be executed. That's the slide I started to talk about with skip. It means you kind of, by contradiction, say, suppose that this can be executed indefinitely and show that this is not fair, so this cannot happen. Okay, that was in the slide skip. So let's assume weak transition fairness. So if I see the same behavior as before, I do that indefinitely. I just keep doing that. See that this transition, let me go back, that transition is this one, right? So I wrote it as transitions here. But you kind of can understand that this is a transition. That is enabled, right? There's no condition, so I can execute it, right? So if I execute it, so if I just do that loop, I can always execute it. So by contradiction, suppose I don't execute it, suppose I don't execute that. If I don't execute that, that would never be enabled, right? That transition is not enabled. So I'm going to loop, and each time I'm just going to select the true. I'm not going to change anything, and it still is enabled. So from the beginning, it's enabled forever. Okay? So there's a contradiction for this to be a good execution. It's not fair, right? It's not weakly fair to that transition. Okay? Weak transition fairness says if some transition is enabled from some point on forever, continuously, it's not fair. So it's a contradiction, because then that is not an execution that can happen. Therefore, this has to happen, right? If I take only the fair executions, if I now, when I do knowledge checking, I want to take only the fair executions, then I can guarantee that this happens. You agree? Okay, yeah? Now let's see what happened. Now I'm doing this loop. And in order to terminate or deadlock, I need y not to be 0, right? So I needed to execute that. But if I do that loop, even infinitely many times, okay, I have a non-deterministic choice here. And in fact, this transition is not continuously enabled. Why it's not continuously enabled? Because when I'm here at the head of the loop, I cannot do that. I'm first checking when the control is here, I'm not here. So it's not enabled now. Now I go here, it is enabled, and then it's not enabled. Enabled, not enabled. It means that it is weakly fair not to take that, because it's not enabled from some point on continuously. It's enabled, not enabled. And so weak fairness does not guarantee that this will be taken. So under weak transition fairness, no guarantee that this will be taken. I can, since it happens infinitely many times but not enabled continuously, it's not guaranteed that this is going to execute forever. Let's see weak process fairness. Weak process fairness says, okay, don't look at transition, look at the process. It says, if a process can execute from some point continuously, then you have to give that process the chance of doing something. So this process is continuously enabled. If I'm here, then it's not fair, because I can always do that. Continuously or not, I can always do that. So this would happen. Again, I look at that process, and that process is going to be enabled now continuously, because this process ended. So I can do some transition of that process. So I select this one, and then I select this one, and this one, and this one, and this. It's okay, it's fair. So it's a fair execution. This didn't have to execute. So I can look at strong process fairness. Okay? Strong process fairness says that if that process, if any process, can execute infinitely many times, it's going to execute infinitely many times. That's it. I mean, if I don't execute this thing, then it is enabled infinitely many times. So by contradiction, I cannot just ignore it. I have to execute it under strong process fairness. Now that process now is the only process which is enabled, and I can execute it infinitely many times by doing this and that, and this and that, and this and that. Again, I'm not guaranteeing to terminate. And if I look now at strong transition fairness, strong transition fairness again would force this to execute. And now it says for every transition, if it can execute infinitely many times, it's going to execute. The differences are very subtle, right? Sometimes hard to see. It says, if I can execute that transition infinitely many times, I'm going to execute. Or again, that slide I skipped. It says, in the contradiction, show that something is not fair and therefore it's not a good execution. So I show you that it's not fair not to execute that. It's not fair, which means that I have to execute it. So let's see, that transition is not continuously enabled because I loop from here to here, right? I loop from outside of the loop to inside of the loop, okay? But I loop infinitely many times. And when I'm here, I have a non-deterministic choice. Now, under this non-deterministic choice, that transition is enabled infinitely many times. So since it's a strong transition fairness, the transition x equals 1, if I don't select it, it's not fair for it, because it's enabled infinitely many times, and it's not executed. So I have to execute it. I set y to 1, and that kills the loop, and then terminated the deadlock, whichever we like. Okay? So you see there are 4 conditions of fairness, and only the strong transition fairness fair. And so, I mean, many people came up with definitions of fairness. And one way to handle that is to write fairness as a temporal formula. So the temporal formula now has to argue not only about states but also about transitions. So suppose you have a predicate that says alpha is executed, alpha is in transition, and then you can write the fairness transitions as formulas, as very complicated formulas. Basically, we don't want to get into it, but like say this one, it says for all the processes Pi, if eventually always, or if continuously, Pi is enabled, which means that one of the transitions in Pi is enabled, then always infinitely many times, always eventually infinitely many times, I execute Pi, which means I execute one of the transitions. This is a huge formula. It has a lot of proposition that talks not only about the state but also about the action that is executed. The size of that formula is as big as the program. Why is it? Because every transition is encoded here, right? And every transition's enabling condition is encoded here. This is not a practical thing to do, but if you like, add that. So instead of proving the property, prove that if it's fair, if the condition for fairness holds, implies, then the property holds. That would give you a really huge formula. It's completely non-practical, but it works. And another possibility is to do the direction. Now there's different strength of fairness, right? So some fairness conditions include each other. Right? And you have to pick up the fairness conditions. So what you want to do is you want to pick up the condition which exclude as least possible execution, because you don't want to exclude too many, but still holds. Now, as I said, it's a modeling issue. You don't always know exactly what happened. A lot of times, the fairness corresponds to some kind of physical properties about the machine. So again, it's a point where you can err when you do the modeling. But you select the fairness, and then instead of checking that the property that corresponds to the fairness implies the property you want to hold, this is model checking a fairness which would work, but the algorithm is too complicated. Instead of that, you can alter the algorithm. So for example, for weak fairness, right? Remember the algorithm was find a path to a strongly connected component, right? That has an accepting state, right? So now I require that the strongly connected component for weak fairness would satisfy that, say it's a weak transition fairness, that the strongly connected component for each transition would satisfy that for every state, either the transition is not enabled or the transition is executed. This is directly encoding the fairness condition on the path. So for weak fairness, weak transition fairness, and weak process fairness, I can do that. For strong fairness, the algorithm is very complicated. It takes the graph and it takes out some edges and gets newer graph, and then it repeatedly shrinks the graph, and it's a very complicated algorithm. Therefore, even in tools like Spin, which I think it's the most popular tool for doing model checking the software, not always all the fairnesses are encoded. So Spin can do weak transition fairness. That's it. If you need strong fairness, Spin doesn't do it. You can still encode the fairness as a formula as I showed here. A huge formula, right? Each one of these, like this one, see, that's already a big disjunction, right? Over the transitions. It's huge. You can do that. People usually don't do that. Another thing is that not everybody believes in strong fairness. Like I don't believe in strong fairness. I don't believe that something would work because someone implemented strong fairness. right? So physically, it has to do with some statistics. So some people believe it is some or not. Again, it depends on you. Now, the main point about this complicated thing is, let's go back to the Decker algorithm. Unfortunately, model checking without fairness sometimes is not strong enough. There are algorithms that depend on fairness, right? So what you need to do is you want to find the correct fairness, or you want to assume some fairness, and still, when you find a counterexample, you want to check it against the actual code, right? And see if it was a real execution or not. Okay? That's the point about fairness. And I think that's it for today because my throat is tricky. So tomorrow we'll see a completely alternative algorithm with another logic, which is called CTL. It's going to be an algorithm that the logic will be branching. The algorithm will be somewhat simpler, and there's no graphs.
太这个精巧。